Imagine standing on the launch pad at Cape Canaveral, strapped into humanity's fastest spacecraft, ready to embark on the ultimate road trip through our solar system. But here's the thing that might blow your mind. Even traveling at speeds that would circle Earth in minutes, reaching our neighboring planets would take months, years, or even decades. Today, we're going on an incredible journey to discover exactly how long it would take to reach each planet in our cosmic neighborhood, using everything from current technology to theoretical propulsion systems that might one day carry our descendants to the stars. If you're fascinated by space exploration, make sure to subscribe to this channel and give a thumbs up. Now let's begin this incredible journey. Before we blast off to explore each planet, we need to understand something fundamental about space travel that science fiction movies never tell you. Space isn't like driving on a highway where you can maintain a constant speed. It's more like sailing across an ocean where the winds and currents constantly change, except these cosmic currents are gravitational fields, and the distances are so vast they make Earth's oceans look like puddles. When we talk about traveling to other planets, we're not taking a straight path. Planets orbit the Sun at different speeds and distances, constantly moving in their cosmic dance. Earth zooms around the Sun at about 67,000 miles per hour, while Neptune creeps along at 12,000 miles per hour. This means the distance between Earth and any other planet is constantly changing. Mars, for instance, can be as close as 34 million miles or as far as 250 million miles, depending on where both planets are in their orbits. This is why space agencies wait for what they call launch windows, specific times when the alignment of planets makes the journey shortest and requires the least fuel. These windows might come only once every few years. Miss your window to Mars? You'll have to wait 26 months for the next optimal opportunity. It's like waiting for two trains on circular tracks to align perfectly before you can jump from one to the other. The speed of our spacecraft is another crucial factor. The fastest human-made object ever created, the Parker Solar Probe, reached speeds of 394,000 miles per hour as it dove toward the Sun. But here's the catch. We achieved that incredible speed by using the Sun's massive gravity as a slingshot. We can't just point a rocket at Neptune and accelerate to those speeds. The amount of fuel required would be astronomical, literally. Currently, our chemical rockets, the workhorses of space exploration, can achieve speeds of about 25,000 miles per hour when escaping Earth's gravity. That might sound fast, and it is by Earth standards. You could fly from New York to Los Angeles in 6 minutes at that speed. But in the vast emptiness of space, where distances are measured in millions and billions of miles, it's like crawling across a continent. Let me paint you a picture of just how empty space really is. If Earth were the size of a marble, the Moon would be a pea about a foot away. Mars, at its closest, would be a smaller marble about 25 feet away. Jupiter would be a softball nearly 200 feet from you. And Neptune? It would be a golf ball over a quarter-mile away. Now imagine trying to flick your Earth marble hard enough to reach that Neptune golf ball. That's essentially what we're trying to do with rockets. The fuel problem is what engineers call the tyranny of the rocket equation. To go faster, you need more fuel. But more fuel means more weight. More weight means you need even more fuel to lift that fuel. It's a vicious cycle that has plagued space exploration since the beginning. The Saturn V rocket that took astronauts to the Moon was about 85% fuel by weight. Only a tiny fraction was actual spacecraft and payload. This is why most interplanetary missions use a technique called the Hohmann transfer orbit, named after the German engineer Walter Hohmann, who figured it out in 1925, decades before we even had rockets capable of reaching space. Instead of flying directly to a planet, spacecraft take an elliptical path that uses the least amount of fuel. It's longer in distance but much more efficient. Think of it like coasting downhill on a bicycle instead of pedaling the whole way. You might take a longer route to find the hills, but you'll arrive less exhausted. Another trick spacecraft use is gravitational assists, or slingshots. By flying close to a planet or moon, a spacecraft can steal some of that body's orbital energy, speeding up without using any fuel. Voyager 2 used gravitational assists from Jupiter, Saturn, Uranus, and Neptune to tour the outer solar system, a grand tour that would have been impossible with rockets alone. It's like a cosmic game of pinball, bouncing from one planet's gravity to another. Now let's talk about Mercury, the innermost planet, our solar system's speed demon. You might think that because Mercury is the closest planet to the Sun, it would be easy to reach. After all, it's only about 48 million miles away at its closest approach to Earth. But here's the cosmic joke. Mercury is actually one of the hardest planets to reach, and it all comes down to orbital mechanics. To reach Mercury, you need to slow down a lot. Earth orbits the Sun at 67,000 miles per hour, while Mercury zips around at 106,000 miles per hour. But here's the counterintuitive part. To fall inward toward the Sun and reach Mercury, you need to cancel out much of Earth's orbital velocity. This requires an enormous amount of fuel, more than it takes to reach Mars or even Jupiter. NASA's Messenger mission, which orbited Mercury from 2011 to 2015, took 6.5 years to reach the planet. Why so long? Messenger couldn't fly directly to Mercury. Instead, it performed a complex series of gravitational assists, 1 flyby of Earth, 2 of Venus, and 3 of Mercury itself, before finally entering orbit. The spacecraft traveled 4.9 billion miles to reach a planet that's only 48 million miles away at its closest. It's like driving from New York to Los Angeles by way of Tokyo. The European Space Agency's Bepi-Colombo mission, currently en route to Mercury, launched in October 2018 and won't enter Mercury orbit until December 2025, a 7-year journey. It's performing an even more complex dance, with 1 Earth flyby, 2 Venus flybys, and 6 Mercury flybys before orbital insertion. The spacecraft is essentially playing cosmic billiards, using planetary gravity to gradually adjust its orbit to match Mercury's. If we could somehow ignore fuel constraints and fly directly to Mercury at our current maximum speeds, the journey would take about 40 days at the closest approach. But that's pure fantasy with our current technology. The fuel required would weigh more than anything we could possibly launch from Earth. This is why reaching Mercury remains one of the most challenging endeavors in planetary exploration. The harsh reality is that Mercury's proximity to the Sun creates another problem: heat. Any spacecraft approaching Mercury must be designed to withstand temperatures exceeding 800 degrees Fahrenheit on the sunlit side, while simultaneously dealing with minus 290 degrees Fahrenheit on the dark side. It's like building a vehicle that can survive both inside a blast furnace and in liquid nitrogen. The technological challenges are immense. Now let's turn our attention to Venus, Earth's so-called twin sister, though she's more like an evil twin with her crushing atmosphere and sulfuric acid rain. Venus is our nearest planetary neighbor, coming as close as 25 million miles during inferior conjunction when Venus passes between Earth and the Sun. At this distance, Venus is the closest any planet gets to Earth, even closer than Mars ever comes. The journey to Venus is actually one of the most straightforward in our solar system. The Soviet Union's Venera program proved this repeatedly, with Venera 1 launching in 1961, just 4 years after Sputnik. Although that first mission failed, subsequent Venera missions successfully reached Venus in about 4 to 5 months. NASA's Mariner. 2. The first successful interplanetary spacecraft took 3.5 months to reach Venus in 1962. Modern missions haven't gotten much faster. NASA's Parker Solar Probe, while not specifically targeting Venus, uses multiple Venus flybys to adjust its orbit around the Sun. Each flyby takes about 4 to 5 months from Earth, consistent with travel times from 60 years ago. This consistency isn't due to lack of technological advancement, but rather the fundamental physics of orbital mechanics. We're still bound by the same equations that govern all objects moving through space. The European Space Agency's Venus Express took about 5 months to reach Venus in 2006, while Japan's Akatsuki took about 7 months in 2010, though it initially failed to enter orbit and had to wait 5 years for another attempt. These missions show that regardless of the space agency or technology level, the journey to Venus remains remarkably consistent in duration. What makes Venus relatively easy to reach isn't just its proximity, but also its orbital characteristics. Venus orbits the Sun every 225 Earth days, and its nearly circular orbit means the distance between Earth and Venus doesn't vary as dramatically as with other planets. Launch windows to Venus occur every 19 months, more frequently than for any other planet except Mars. If we could develop more advanced propulsion systems, the trip to Venus could be shortened considerably. With nuclear electric propulsion, which NASA is currently developing, we might reach Venus in 2 to 3 months. With theoretical fusion rockets, the journey could be reduced to just a few weeks, but even with our current chemical rockets, Venus remains one of the most accessible destinations in our solar system. The real challenge with Venus isn't getting there, it's surviving once you arrive. The Soviet Union learned this the hard way. Their early Venera landers were crushed by atmospheric pressure 90 times greater than Earth's, like being under 3,000 feet of ocean water. The temperature at the surface, 900 degrees Fahrenheit, is hot enough to melt lead. The atmosphere is so thick that walking on Venus would feel like walking through water, except the water is made of carbon dioxide laced with sulfuric acid. Despite these challenges, Venus remains a tantalizing target for future exploration. Some scientists have proposed floating cities in Venus's upper atmosphere, where temperatures and pressures are much more Earth-like. At an altitude of 30 miles above the surface, the temperature drops to about 160 degrees Fahrenheit, and the pressure equals that on Earth. Humans could theoretically live there in balloon-like habitats, floating above the hellish surface in the relatively calm upper atmosphere. Now we come to Mars, the red planet, humanity's obsession, and perhaps our future second home. Mars has captured our imagination like no other planet, and for good reason. It's the most Earth-like planet in our solar system, with a day length almost identical to Earth's and evidence of ancient rivers, lakes, and possibly oceans. But reaching Mars is where the real challenge of interplanetary travel becomes apparent. The distance to Mars varies more dramatically than any inner planet. At its closest approach, called opposition, Mars can be as near as 34.8 million miles. At its farthest, when Mars is on the opposite side of the Sun, it's about 250 million miles away. This vast difference in distance significantly affects travel time and mission planning. Speaking of vast distances, if you're curious about just how enormous our solar system really is and want to understand these planetary distances in perspective, I created a video called How Big is the Solar System that will absolutely blow your mind. The link is in the description below and pinned on the comments. Trust me, after watching that, these journey times will make a lot more sense. The optimal time to launch a mission to Mars occurs roughly every 26 months, when Earth and Mars align properly. This alignment, called a Mars transfer window, allows spacecraft to use a Hohmann transfer orbit, that fuel-efficient elliptical path I mentioned earlier. Miss this window and you'll either need significantly more fuel or wait over 2 years for the next opportunity. NASA's recent success stories demonstrate typical Mars travel times. The Perseverance rover, launched in July 2020, took about 7 months to reach Mars, landing in February 2021. This 7-month journey is fairly standard for Mars missions using current technology. NASA's InSight lander also took about 7 months, as did the Mars Science Laboratory, carrying the Curiosity rover. The fastest journey to Mars using current technology was achieved by NASA's Mariner 7 in 1969, which took just 128 days, about 4 months. However, this was a flyby mission, not designed to enter orbit or land. When you need to slow down enough to enter Mars orbit or land on the surface, you need to carry more fuel, which means a heavier spacecraft and a longer journey. SpaceX's Elon Musk has claimed his Starship could potentially reduce the journey to Mars to as little as 3 months, possibly even 80 days with favorable conditions. This would require advances in propulsion technology and accepting higher speeds that would require more fuel to slow down at Mars. The trade-off between speed and fuel consumption remains one of the fundamental challenges of Mars exploration. The human factor adds another layer of complexity to Mars travel. While robotic missions can take the slow, fuel-efficient route, human missions need to minimize travel time to reduce radiation exposure and psychological stress. Astronauts traveling to Mars would be exposed to cosmic radiation for months, receiving a dose equivalent to getting a full-body CT scan every 5 to 6 days. This radiation exposure is one of the biggest health risks for Mars travelers. The psychological challenges are equally daunting. Imagine being confined in a spacecraft no larger than a small house, with a few other people for 7 months, knowing that Earth is getting farther away every day. Communication delays would grow from minutes to over 20 minutes each way at maximum distance. If something goes wrong, there's no possibility of rescue or quick return. It's isolation on a scale no human has ever experienced. Despite these challenges, Mars remains our most viable option for establishing a self-sustaining colony beyond Earth. The planet has water ice at its poles and possibly underground, carbon dioxide in its atmosphere that could be converted to oxygen, and soil that might be modified to grow crops. The journey might be long and dangerous, but the destination offers the possibility of becoming a true second home for humanity. Now let's venture into the realm of the gas giants, starting with Jupiter, the king of planets. Jupiter is a monster, more massive than all other planets combined, with a gravitational field so strong it acts like a cosmic vacuum cleaner, protecting Earth from many potential asteroid and comet impacts. But reaching Jupiter requires a fundamental shift in how we think about space travel. The distance to Jupiter ranges from 365 million miles at its closest to 600 million miles at its farthest. These distances are so vast that even light, the fastest thing in the universe, takes between 33 and 53 minutes to travel from Jupiter to Earth. When mission controllers send commands to spacecraft at Jupiter, they're essentially communicating with the past. NASA's Galileo mission, launched in October 1989, took 6 years to reach Jupiter, arriving in December 1995. But Galileo didn't take a direct route. It performed gravitational assists around Venus once and Earth twice, building up the speed necessary to reach Jupiter's orbit. This indirect path actually saved fuel and allowed the spacecraft to carry more scientific instruments. The Juno mission, currently orbiting Jupiter, took a more direct route but still required 5 years to reach the giant planet. Launched in August 2011, Juno arrived at Jupiter in July 2016. Despite advances in technology since Galileo, the travel time didn't decrease significantly because we're still limited by the fundamental physics of chemical rockets. The fastest journey to Jupiter was achieved by NASA's New Horizons spacecraft, which reached Jupiter in just 13 months. But New Horizons wasn't stopping at Jupiter. It was using the giant planet's gravity as a slingshot to reach Pluto. Because it didn't need to slow down and enter orbit, New Horizons could maintain its incredible speed of 36,000 miles per hour relative to the Sun. The European Space Agency's JUICE mission, launched in April 2023, won't reach Jupiter until July 2031, an 8-year journey. JUICE is taking a complex route involving gravitational assists from Earth, Venus, and Earth again, then Mars, and finally Earth one more time before heading to Jupiter. This cosmic pinball game saves fuel but dramatically increases travel time. What makes Jupiter particularly challenging isn't just the distance, but also its intense radiation environment. Jupiter's magnetic field is 20,000 times stronger than Earth's, creating radiation belts that would kill an unprotected human in minutes. Any future human mission to Jupiter's system would likely target its moons, particularly Europa or Ganymede, which orbit outside the worst of the radiation belts. Europa, with its subsurface ocean beneath an icy crust, is one of the most promising places in our solar system to search for life. But reaching Europa adds another layer of complexity. After the years-long journey to Jupiter, a spacecraft must then navigate through Jupiter's system of moons, each with its own gravitational field. NASA's upcoming Europa Clipper mission, launching in October 2024, will take 5.5 years to reach Jupiter, then spend 4 years performing multiple flybys of Europa rather than orbiting it directly. The possibility of using Jupiter's moons as stepping stones for human exploration has fascinated scientists for decades. Callisto, the outermost of Jupiter's 4 large moons, sits far enough from Jupiter to avoid the worst radiation. It could potentially serve as a base for exploring the entire Jovian system, but even with a base on Callisto, the round-trip communication delay with Earth would be between 1 and 2 hours, making real-time support impossible. Future propulsion technologies could dramatically reduce travel time to Jupiter. Nuclear electric propulsion could cut the journey to about 2 to 3 years. Theoretical fusion rockets might reduce it to less than a year. But even these advanced technologies face the challenge of slowing down once they reach Jupiter. The faster you go, the more energy you need to brake, and Jupiter's enormous gravity makes this particularly challenging. Now we journey even farther out to Saturn, the jewel giant with its spectacular ring system. Saturn orbits between 800 million and 1 billion miles from Earth, depending on our relative positions. At these distances, we're entering the realm where space travel becomes a test of patience and engineering endurance. The Cassini-Huygens mission remains our most successful exploration of Saturn. Launched in October 1997, Cassini took nearly 7 years to reach Saturn, arriving in July 2004. Like many outer solar system missions, Cassini used multiple gravitational assists, 2 from Venus, 1 from Earth, and 1 from Jupiter, to gain the necessary speed. The spacecraft traveled a total of 2.2 billion miles to reach Saturn, even though the straight-line distance was less than half that. Cassini's journey illustrates a fundamental trade-off in space exploration. We could theoretically reach Saturn faster with a more powerful rocket and a direct trajectory, but this would require enormous amounts of fuel. By taking a longer, indirect route and using planetary flybys, Cassini could carry more scientific instruments and fuel for its 13-year exploration of the Saturn system. The Voyager missions provided our first close-up views of Saturn and demonstrated the efficiency of the Grand Tour trajectory. Voyager 1 reached Saturn in November 1980, just 3 years after launch, while Voyager 2 arrived in August 1981, 4 years after launch. These relatively quick transit times were possible because the Voyagers were on flyby missions, not stopping to orbit Saturn. What Cassini revealed about Saturn's moon Titan makes the long journey potentially worthwhile for future human exploration. Titan has a thick atmosphere, lakes and rivers of liquid methane, and complex organic chemistry. It's the only moon in our solar system with a substantial atmosphere and the only body besides Earth with stable liquid on its surface. Some scientists consider Titan even more interesting than Mars as a potential site for human colonization. The Dragonfly mission, scheduled to launch in 2027, will send a nuclear-powered drone to explore Titan's surface. The journey will take about 7 years, arriving in 2034. Dragonfly will be able to fly from location to location on Titan, taking advantage of the Moon's thick atmosphere and low gravity. It's an ambitious mission that shows how our exploration strategies are evolving beyond simple orbiters and landers. Saturn's distance from the Sun creates unique challenges for spacecraft power. At Saturn's distance, solar panels receive only 1% of the sunlight they would at Earth. This is why many outer solar system missions rely on radioisotope thermoelectric generators, which convert heat from radioactive decay into electricity. These nuclear batteries can operate for decades, as demonstrated by the Voyager spacecraft, still functioning after more than 45 years in space. Moving outward to Uranus, we enter the realm of the ice giants, a fundamentally different class of planet from the gas giants Jupiter and Saturn. Uranus orbits between 1.6 and 1.9 billion miles from Earth, distances so vast that only one spacecraft has ever visited this tilted world. The journey to Uranus represents one of the greatest challenges in planetary exploration, Voyager 2 remains our only close encounter with Uranus, flying past the planet in January 1986, 8.5 years after launch. This single flyby, lasting just hours, provided nearly everything we know about Uranus from close range. The spacecraft discovered new rings, new moons, and revealed Uranus's bizarre magnetic field, tilted 60 degrees from its rotation axis. NASA has proposed several missions to Uranus over the decades, but the journey time remains a major obstacle. A dedicated orbital mission to Uranus would take between 10 and 15 years with current technology, depending on the trajectory and whether gravitational assists are used. The Uranus Orbiter and Probe mission, identified as a priority by the planetary science community, would launch in the early 2030s and arrive in the 2040s. The extreme distance to Uranus creates communication challenges that dwarf those faced at Mars or even Jupiter. Radio signals take between 2.5 to 3 hours to travel from Uranus to Earth. This means a round-trip communication would take 5 to 6 hours. If something goes wrong during orbital insertion or probe deployment, mission controllers would be helpless, learning about problems hours after they occurred. Uranus's unique characteristics make it worth the long journey. The planet is tilted on its side, rotating at a 98-degree angle to its orbit. This extreme tilt, possibly caused by a massive collision early in its history, creates bizarre seasons where each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. Understanding how this affects the planet's atmosphere and magnetosphere could revolutionize our understanding of planetary dynamics. The ice giants represent a common type of planet in our galaxy, based on exoplanet discoveries. By studying Uranus up close, we could better understand thousands of similar worlds orbiting other stars. But the journey time remains daunting. Even with nuclear electric propulsion, a mission to Uranus would take 6 to 8 years. Breakthrough propulsion technologies would be needed to make regular exploration of Uranus feasible. Finally, we reach Neptune, the windiest planet in our solar system and the most distant of the major planets. Neptune orbits at an average distance of 2.8 billion miles from the Sun, but its distance from Earth varies from 2.7 to 2.9 billion miles. These are numbers so large they lose meaning. At its closest, Neptune is still about 30 times farther from the Sun than Earth. Voyager 2's flyby of Neptune in August 1989, 12 years after launch, remains our only close encounter with this deep blue world. The spacecraft discovered the Great Dark Spot, a storm system the size of Earth, and Triton's nitrogen geysers, shooting dark material 5 miles high in the thin atmosphere. These discoveries from a brief flyby hint at the complexity waiting to be discovered. A dedicated mission to Neptune faces even greater challenges than one to Uranus. The proposed Neptune Odyssey mission would take between 12 and 15 years to reach Neptune using conventional propulsion and gravitational assists. The spacecraft would need to function perfectly for over a decade in the harsh environment of deep space before even beginning its primary mission. The sheer distance to Neptune creates problems beyond just travel time. Solar panels are useless at Neptune's distance. The Sun appears just as a bright star, providing only 1/1000th the light it does at Earth. Any mission must carry nuclear power sources, adding weight, complexity, and political challenges to mission planning. The radioactive plutonium needed for these generators is in limited supply, making each outer planet mission a precious resource. Communication with a spacecraft at Neptune pushes our technology to its limits. Radio signals traveling at the speed of light take 4 hours to travel from Neptune to Earth. Imagine trying to drive a car where every turn of the steering wheel takes 8 hours to show its effect. This is the reality of controlling a spacecraft at Neptune. Mission planners must anticipate problems and program solutions years in advance. Neptune's moon Triton adds another compelling reason to make the long journey. Triton orbits Neptune backward, suggesting it was captured from the Kuiper Belt. It's geologically active, with nitrogen geysers indicating internal heat. Some scientists suspect Triton might harbor a subsurface ocean, making it another potential abode for life. But exploring Triton means first enduring the 12 to 15-year journey to Neptune, then navigating the complex gravitational environment of the Neptune system. The future of Neptune exploration might lie in breakthrough propulsion technologies. Fusion rockets, still theoretical, could potentially reduce travel time to Neptune to 3 to 4 years. Antimatter propulsion, even more speculative, might cut it to months. But these technologies remain decades away from practical application. For now, Neptune remains the frontier, visited once by humanity and waiting patiently for our return. Now let's talk about the dwarf planet that started as the 9th planet and captured hearts worldwide, Pluto. When New Horizons launched in January 2006, Pluto was still officially a planet. By the time it arrived in July 2015, Pluto had been reclassified as a dwarf planet. The 9.5-year journey to Pluto represents one of humanity's greatest achievements in space exploration. New Horizons holds the record as the fastest spacecraft ever launched, leaving Earth at 36,000 miles per hour. Even at this incredible speed, reaching Pluto took nearly a decade. The spacecraft traveled 3 billion miles, assisted by Jupiter's gravity, to reach this frozen world at the edge of our solar system. During most of its journey, New Horizons was in hibernation mode, waking periodically for system checks. What New Horizons revealed made the long wait worthwhile. Pluto isn't the dead, frozen world we expected. It has nitrogen glaciers, water ice mountains as tall as the Rockies, and a thin atmosphere that freezes and falls as snow when Pluto moves away from the Sun. The heart-shaped Tombaugh Regio became instantly iconic, showing that even at the edge of our solar system, worlds can be geologically complex and beautiful. The distance to Pluto varies enormously due to its elliptical orbit. At its closest to the Sun, Pluto is about 2.7 billion miles from Earth. At its farthest, it's over 4.6 billion miles away. This variation, combined with Pluto's 248-year orbit, means that optimal launch windows are rare. Miss one, and you might wait decades for another good opportunity. future missions to Pluto face a dilemma. New Horizons performed a flyby, gathering data during a brief encounter. An orbital mission would provide far more science but would require massive amounts of fuel to slow down and enter orbit around Pluto. This would make the spacecraft heavier, the journey longer, and the mission far more expensive. With current technology, an orbital mission to Pluto might take 15 to 20 years. But here's something mind-blowing to consider. When New Horizons was launched, the best images of Pluto were pixelated blobs from the Hubble Space Telescope. Children born when New Horizons launched were in 4th grade when it finally reached Pluto. This is the reality of outer solar system exploration with current technology, missions that span significant portions of human lifetimes. Now let's dream about the future of interplanetary travel. Everything I've told you so far assumes chemical rockets, the technology we've been using since the dawn of the space age. But revolutionary propulsion technologies are in development that could transform these journey times from years to months or even weeks. Nuclear thermal propulsion, which NASA is actively developing, could double or triple the efficiency of chemical rockets. Instead of burning fuel with oxidizer, nuclear thermal rockets heat hydrogen with a nuclear reactor, shooting it out the back at much higher speeds. A spacecraft with nuclear thermal propulsion could reach Mars in 3 to 4 months instead of 7, and Jupiter in 2 to 3 years instead of 5 or 6. Nuclear electric propulsion, also called ion drives, is already being used on some spacecraft. These engines use electricity from nuclear reactors to accelerate ions to incredible speeds, 10 times faster than chemical rocket exhaust. While the thrust is tiny, it can be maintained for years, gradually building up enormous velocities. The Dawn spacecraft used ion propulsion to visit both Vesta and Ceres, something impossible with chemical rockets. Fusion propulsion remains the holy grail of space travel. By fusing hydrogen into helium, the same process that powers the Sun, fusion rockets could achieve exhaust velocities 20 times higher than chemical rockets. A fusion-powered spacecraft could reach Mars in 30 to 45 days, Jupiter in 4 months, and Neptune in 2 years. But fusion propulsion remains decades away from practical application. Even more exotic concepts exist on the drawing board. Breakthrough Starshot proposes using powerful lasers to push tiny spacecraft to 20% the speed of light. While designed for interstellar missions, similar technology could revolutionize solar system travel. Imagine reaching Pluto in just 2 months or Neptune in 3 weeks. The entire solar system would become as accessible as international air travel is today. Solar sails offer another intriguing possibility. By using the pressure of sunlight itself for propulsion, solar sails require no fuel. The Japanese Icaros mission and the Planetary Society's Light Sail projects have demonstrated this technology. While acceleration is slow, solar sails could eventually reach very high speeds, particularly for missions to the outer solar system, where slowing down isn't required. But perhaps the most exciting development is SpaceX's Starship and the concept of orbital refueling. By refueling spacecraft in Earth orbit, we can send much larger payloads to other planets or reach them faster. Starship could potentially carry 100 people to Mars, establishing a genuine colony rather than just scientific outposts. This isn't science fiction. Starship is conducting test flights right now. The psychological and biological challenges of long-duration spaceflight are driving innovation in life support systems. Closed-loop life support, where everything is recycled, could make long journeys more feasible. Artificial gravity through rotating spacecraft sections could prevent bone loss and muscle atrophy. Hibernation or suspended animation, still science fiction but actively researched, could make years-long journeys feel like weeks to the crew. Let me share something that puts all these journey times in perspective. Light, the fastest thing in the universe, takes 8 minutes and 20 seconds to travel from the Sun to Earth. It takes over 4 hours to reach Neptune. If you could travel at light speed, which physics tells us is impossible for anything with mass, you could reach Mars in just 4 minutes at its closest approach. Jupiter would be 33 minutes away. Even at light speed, exploring our solar system would take hours, but we're not traveling at light speed. We're crawling through space at speeds that would seem impossibly fast on Earth, but are agonizingly slow given the distances involved. The Voyager spacecraft, humanity's most distant ambassadors, have been traveling for over 46 years and have only recently entered interstellar space. At their current speed, it would take them 40,000 years to reach the nearest star beyond our Sun. This brings us to a profound realization about our place in the cosmos. Our solar system, which seems so vast that we measure distances in billions of miles, is just a tiny bubble in an ocean of emptiness. The challenges we face reaching Neptune or Pluto pale in comparison to the challenge of reaching another star. We're like islanders who've just learned to build canoes, gazing at distant continents across an infinite ocean. Yet there's something beautifully human about our determination to explore despite these vast distances. Every spacecraft we send is a message in a bottle, carrying our curiosity and wonder across the cosmic sea. The scientists who design these missions often spend entire careers waiting for their spacecraft to reach their destinations. Imagine dedicating your professional life to a mission that won't arrive until you're retired or possibly gone. Consider the team that built New Horizons. Many of the engineers and scientists who designed and built the spacecraft in the late 1990s and early 2000s were at different stages of their careers, or even retired by the time it reached Pluto in 2015. Graduate students who worked on the mission became senior scientists. Children born when it launched were teenagers when it arrived. This is the generational nature of outer solar system exploration. The communication delays I've mentioned create surreal situations for mission controllers. When the Cassini spacecraft plunged into Saturn's atmosphere in September 2017, ending its 20-year mission, the signals telling us about its final moments took 83 minutes to reach Earth. Cassini had been dead for over an hour before we knew it. Mission controllers were essentially watching a recording of events that had already happened, powerless to change the outcome. This time, delay fundamentally changes how we operate spacecraft in the outer solar system. Every command must be carefully planned and tested because mistakes can't be quickly corrected. When New Horizons flew past Pluto, it was operating on a program uploaded weeks in advance. If something had gone wrong during the flyby, there was no way to fix it in real time. The spacecraft had to be smart enough to handle problems on its own. Let's talk about what these journey times mean for human exploration. A round trip to Mars, even with optimal alignment and advanced propulsion, would take at least 18 months, 6 months there, 6 months back, and 6 months waiting for the planets to realign for the return journey. That's assuming everything goes perfectly and uses technology we don't quite have yet. For Jupiter's moons, we're talking about a 4 to 6 year round trip with current technology, possibly 2 to 3 years with advanced propulsion. Saturn, 8 to 12 years round trip. These aren't vacations or even extended deployments like we see on the International Space Station. These are significant portions of human lives spent in small spacecraft far from Earth. The radiation exposure during these journeys is sobering. NASA estimates that a round trip to Mars would expose astronauts to about 600 millisieverts of radiation, about 60 times the annual limit for radiation workers on Earth. A journey to Jupiter would be even worse due to its intense radiation belts. We'd need revolutionary shielding technology or much faster spacecraft to make these journeys survivable. Food and water present another challenge. Every pound of supplies launched from Earth costs thousands of dollars. A crew of 6 traveling to Jupiter would need roughly 50,000 pounds of food and water for the journey, assuming no recycling. With recycling systems like those on the International Space Station, this might be reduced to 10,000 pounds, but that's still a massive amount to accelerate to interplanetary speeds. The psychological challenges might be even greater than the physical ones. Imagine watching Earth shrink to a point of light, knowing that everyone and everything you've ever known is on that tiny dot. Communication delays would make normal conversation impossible. A question to mission control from Jupiter would take an hour to get there and an hour for the response to come back. You'd be truly alone in a way no human has ever experienced. Yet despite these challenges, private companies and space agencies are seriously planning human missions to Mars and possibly beyond. SpaceX's Elon Musk talks about making humanity a multiplanetary species. NASA's Artemis program aims to establish a permanent presence on the Moon as a stepping stone to Mars. China and Russia have announced plans for lunar bases and Mars missions. The journey times might be long, but humanity's ambition reaches even farther. The development of in situ resource utilization, using materials found on other planets, could revolutionize space travel. Instead of carrying all fuel from Earth, missions could manufacture fuel on Mars from its carbon dioxide atmosphere and water ice. This would dramatically reduce the amount of mass that needs to be launched from Earth, making missions more feasible and potentially shortening journey times by allowing for faster trajectories. Asteroid mining could provide another game changer. Many asteroids contain water ice that could be converted to rocket fuel. Imagine fuel depots scattered throughout the solar system, like gas stations on an interstate highway. Spacecraft could travel faster, knowing they can refuel along the way instead of carrying all their fuel from Earth. The asteroid Psyche, which NASA is currently sending a mission to study, might contain enough metal to be worth $10,000 quadrillion, more than Earth's entire economy. But here's a mind-bending thought. As we develop life extension technologies, the perception of these journey times might change. If humans regularly live to 150 or 200 years, a 10-year journey to Saturn might not seem as daunting. It would be like how we view a year-long deployment today, long but manageable. The convergence of space technology and biotechnology might make the outer solar system more accessible than we imagine. Virtual reality and artificial intelligence could also transform long-duration space travel. Imagine spending the journey to Jupiter in immersive virtual worlds, maintaining social connections with Earth through VR despite the communication delay. AI companions could provide real-time interaction when human communication is impossible due to distance. The physical journey might take years, but the psychological experience could be made bearable or even enriching. The discovery of potentially habitable exoplanets has added urgency to developing faster propulsion systems. We've found thousands of planets orbiting other stars, some in the habitable zone where liquid water could exist. But the nearest potentially habitable exoplanet, Proxima Centauri b, is 4.2 light-years away. With current technology, reaching it would take over 70,000 years. Even reaching the outer planets of our own solar system quickly would be a stepping stone to interstellar travel. Let me tell you about something that showcases human ingenuity in dealing with these vast distances: gravity assists. When Voyager 2 launched in 1977, mission planners took advantage of a rare planetary alignment that occurs only once every 176 years. Jupiter, Saturn, Uranus, and Neptune were positioned so that a single spacecraft could visit all four, using each planet's gravity to slingshot to the next. This grand tour trajectory turned what would have been 4 separate missions requiring decades into a single 12-year journey. Voyager 2 gained so much speed from Jupiter's gravity that it cut years off its travel time to Saturn. Saturn then flung it toward Uranus, and Uranus toward Neptune. It's like a cosmic bank shot in billiards, using the motion of the planets themselves to propel our spacecraft across billions of miles. The mathematics behind gravity assists is elegant and counterintuitive. As a spacecraft falls toward a planet, it speeds up, gaining kinetic energy. You might think it would lose that energy as it climbs away from the planet, ending up at the same speed it started. But here's the key: the planet is moving too. The spacecraft steals a tiny bit of the planet's orbital energy, gaining speed while the planet loses an infinitesimally small amount. Jupiter's mass is so enormous that Voyager's theft of energy slowed Jupiter's orbit by about 1 foot per trillion years. This technique has become essential for outer solar system exploration. The Galileo mission to Jupiter used gravity assists from Venus once and Earth twice. Cassini used Venus twice, Earth once, and Jupiter once to reach Saturn. Without these assists, these missions would have been impossible with the rockets available. It's a perfect example of using the solar system's own dynamics to overcome our technological limitations. But gravity assists come with trade-offs. They require precise timing and specific planetary alignments. Miss your window and you might wait years or decades for another opportunity. They also extend mission duration, sometimes adding years to reach the destination. The Bepi-Colombo mission to Mercury, for instance, is taking 7 years instead of a direct path that might take months, but the direct path would require impossibly large amounts of fuel. Now let's consider what these journey times mean for the search for life in our solar system. We've identified several worlds that might harbor life: Mars, Europa, Enceladus, Titan, and possibly Venus's upper atmosphere. But confirming life requires sophisticated instruments, multiple visits, and possibly sample return missions. Each mission represents years or decades of travel time. Europa, Jupiter's ice-covered moon, is perhaps our best bet for finding life beyond Earth. Beneath its frozen surface lies an ocean containing twice as much water as all Earth's oceans combined. The Hubble Space Telescope has detected what appear to be water plumes erupting from Europa's surface, suggesting we might be able to sample its ocean without drilling through miles of ice. But getting there takes 5 to 6 years with current technology. NASA's Europa Clipper mission, launching in 2024, will reach Jupiter in 2030. It will then spend 4 years performing 49 flybys of Europa, building up a comprehensive picture of this potentially habitable moon. By the time the mission concludes, over a decade will have passed since launch. Scientists who design instruments for the mission might retire before seeing their full results. Enceladus, Saturn's small moon, surprised everyone when Cassini discovered it was shooting geysers of water into space from its subsurface ocean. These geysers contain organic molecules, the building blocks of life. Flying through these plumes, we could sample an alien ocean without landing, but Saturn is twice as far as Jupiter. A dedicated Enceladus mission would take 7 to 10 years just to arrive. Titan presents different possibilities. With its thick atmosphere and lakes of liquid methane, it might host a completely different form of life based on different chemistry than Earth life. The Dragonfly mission will explore Titan starting in 2034, but it's taking 7 years just to get there. If Dragonfly discovers something promising, a follow-up mission wouldn't arrive until the 2040s at the earliest. The journey times to these potentially habitable worlds raise profound questions about planetary protection. We must ensure our spacecraft don't contaminate these worlds with Earth microbes, which could both destroy potential alien ecosystems and confuse our search for indigenous life. But sterilization adds complexity and cost to missions. Every component must withstand harsh sterilization procedures while maintaining functionality for decades-long journeys. Sample return missions multiply these challenges. Bringing samples from Mars back to Earth requires not just getting to Mars, but launching a rocket from Mars's surface, something never done before, and then returning to Earth. The Mars Sample Return mission, currently in planning, involves multiple spacecraft and will take over a decade from start to finish. Samples collected by the Perseverance rover in 2021 might not reach Earth until the mid-2030s. For outer planet moons, sample return seems almost impossible with current technology. A mission to collect samples from Europa or Enceladus and return them to Earth would take 15 to 20 years minimum. The samples would need to be kept frozen and protected from radiation during the entire journey. The scientific team that sends the mission might be a completely different group from those who analyze the samples decades later. This generational nature of space exploration requires a different mindset from typical human endeavors. Cathedral builders in medieval Europe worked on projects they knew they wouldn't live to see completed. Similarly, space scientists and engineers must embrace projects that span entire careers. A graduate student who helps design a Neptune mission might be near retirement when it arrives. The vast distances in our solar system also affect how we think about colonization. Mars, our nearest potentially colonizable neighbor, requires a 6 to 9 month journey. That's manageable, similar to how long it took to sail from Europe to Australia in the 1800s, but establishing colonies on Jupiter's or Saturn's moons would be like trying to colonize Antarctica before inventing airplanes. Technically possible, but practically extremely difficult. Consider the logistics of maintaining a colony on Titan. Supply runs would take 7 to 10 years round trip. Communications would have over an hour delay each way. If something goes catastrophically wrong, help is years away. The colony would need to be completely self-sufficient from day one, able to produce its own food, water, air, and equipment. Any critical component that breaks must be fixable with local resources. Yet the scientific rewards of exploring these distant worlds justify the long journeys. Every spacecraft we've sent to the outer planets has revolutionized our understanding. Voyager discovered active volcanoes on Io, organic chemistry on Titan, and the complex dynamics of planetary rings. Galileo revealed Europa's subsurface ocean. Cassini showed us the geysers of Enceladus and the methane cycle on Titan. Juno is rewriting our understanding of Jupiter's interior structure. New Horizons' flyby of Pluto exemplifies how a few hours of close observation can transform our knowledge. Before 2015, Pluto was a fuzzy dot even in our best telescopes. After a 9-year journey for just a few hours of close encounter, we discovered nitrogen glaciers, water ice mountains, a complex atmosphere, and geological activity on a world we thought would be dead. Those few hours justified nearly a decade of waiting. The timescales involved in planetary exploration are teaching us patience and long-term thinking rare in modern society. While social media operates on seconds and politics on election cycles, space exploration operates on decades. This forces us to think beyond immediate gratification, to invest in futures we might not personally see, to work toward goals larger than individual careers or even lifetimes. International cooperation becomes essential when missions take decades. The Cassini-Huygens mission was a collaboration between NASA, the European Space Agency, and the Italian Space Agency. The mission lasted 20 years from launch to end, spanning multiple changes in government, economic recessions, and shifting political priorities. Yet the partnership held, demonstrating that humanity can work together on long-term goals despite short-term differences. Private companies are now entering deep space exploration, potentially accelerating development. SpaceX's Starship, Blue Origin's New Glenn, and other commercial vehicles could dramatically reduce launch costs, making more ambitious missions feasible. If launching mass to orbit becomes 10 times cheaper, suddenly nuclear propulsion and massive spacecraft become affordable. Journey times that seem fixed by physics might be overcome by economics and innovation. The development of artificial intelligence and autonomous systems is becoming crucial for deep space exploration. When your spacecraft is hours away by radio signal, it can't wait for instructions from Earth to handle emergencies. Future missions will need AI systems capable of diagnosing problems, making repairs, and even conducting scientific observations without human intervention. Imagine a spacecraft smart enough to notice something unexpected and investigate it without being told. This autonomy is already being tested. The Mars rovers use AI to select interesting rocks to study when communication windows with Earth are closed. The Mars helicopter Ingenuity makes split-second decisions about where to land based on terrain it's never seen before. As we venture farther into the solar system, our robotic explorers will need even greater independence, essentially becoming artificial scientists exploring on humanity's behalf. Let me share something that highlights how journey times affect mission planning. When scientists propose a mission to a distant planet, they must predict what technology will be available not just at launch, but when the spacecraft arrives decades later. Imagine designing a computer system today that needs to work perfectly in 2040 without any physical upgrades. The processors on New Horizons were designed in the 1990s, but had to function flawlessly in 2015 and beyond. This creates a paradox. Missions using proven, reliable technology might be overtaken by faster missions using newer technology launched years later. A spacecraft launched to Neptune today might arrive after one launched 5 years from now with better propulsion. This weight calculation torments mission planners. Do you launch now with existing technology or wait for something better that might never materialize? The biological effects of long-duration spaceflight are still being discovered. We know about bone loss, muscle atrophy, and radiation exposure, but what about the psychological effects of watching Earth fade to invisibility? What happens to human cognition after years in confined spaces? Some scientists propose that crews traveling to the outer planets might need to be put in suspended animation, not for the science fiction reason of making the journey seem shorter, but to preserve their physical and mental health. Recent experiments on the International Space Station have revealed unexpected challenges. Astronauts' vision changes in microgravity due to fluid shifts in the brain. Their gut microbiome alters, even their DNA expression changes. These effects, after just months in space, raise serious questions about years-long journeys to Jupiter or Saturn. We might need to redesign humans through genetic engineering or cybernetic enhancements to make them suitable for deep space travel. The concept of generation ships becomes relevant when considering the outer planets. While not necessary for our solar system, the technologies and social structures needed for multi-generational space travel might first be tested on journeys to Neptune or the Kuiper Belt. Imagine a spacecraft where the crew that arrives at the destination are the grandchildren of those who departed Earth. It sounds like science fiction, but it might be more practical than trying to preserve a single crew for decades. Here's a fascinating consideration: time dilation. While the effects are tiny at the speeds we can currently achieve, they're measurable. Astronauts on the International Space Station age slightly slower than people on Earth, about 1/100th of a second per year. On a high-speed journey to Pluto, astronauts might age a few seconds less than those on Earth. It's negligible now, but future propulsion systems approaching significant fractions of light speed would make time dilation a real factor in mission planning. The economics of planetary exploration shapes everything. A mission to Mars costs roughly $2 to $3 billion. A mission to Jupiter costs $4 to $5 billion. A mission to Neptune might cost $7 to $10 billion. These aren't just numbers. They represent thousands of jobs, years of development, and political capital that must be maintained across multiple administrations. When a mission takes 20 years from conception to completion, it must survive multiple economic cycles and changing political priorities. This economic reality means we must choose our destinations carefully. Every mission to Neptune means perhaps 3 missions to Mars that don't happen. This creates fierce competition within the scientific community. Should we focus on potentially habitable worlds? Worlds that tell us about solar system formation? Worlds with unique characteristics that challenge our theories? The journey times factor heavily into these decisions. A faster mission might provide less science but deliver results within a reasonable time frame. The role of international collaboration becomes even more critical as journeys get longer and more expensive. The proposed ice giants mission to Uranus or Neptune would likely require NASA, ESA, and other agencies working together, sharing costs and expertise. No single nation might be willing to fund a 15-year mission alone, but together the investment becomes manageable. These collaborations, forced by the vast distances involved, might help unite humanity around common goals. Commercial mining of asteroids and moons could transform journey times by providing fuel and resources throughout the solar system. Instead of carrying everything from Earth, missions could refuel at Ceres, resupply at Mars, or even manufacture spare parts at Jupiter's moon Callisto. This distributed infrastructure would make the solar system feel smaller, turning impossible journeys into merely difficult ones. The discovery of interstellar objects like Oumuamua and Borisov passing through our solar system adds urgency to developing faster propulsion. These visitors from other star systems spend only months in our neighborhood before disappearing forever. Oumuamua was already leaving when we discovered it. With current technology, we had no hope of catching it. But with fusion rockets or other advanced propulsion, we might be able to intercept future interstellar visitors, potentially learning about other solar systems without leaving our own. Space elevators, if they prove feasible, could revolutionize planetary exploration by dramatically reducing the cost of reaching orbit. Most of the energy in space travel is spent just getting off Earth. A space elevator would make launching interplanetary missions as routine as taking an elevator to your office. Suddenly, those multi-year journeys to Jupiter become more palatable when the ticket price drops from billions to millions. The development of closed ecological systems will be essential for long-duration missions. We need miniature Earths, spacecraft that recycle everything, growing food, purifying water, and refreshing air without any resupply from Earth. Experiments like Biosphere 2 have shown how difficult this is. But solving these challenges for a journey to Saturn would also help us live more sustainably on Earth, creating technologies that benefit everyone. Nuclear pulse propulsion, once studied in the 1960s under Project Orion, could provide enormous speeds by detonating nuclear bombs behind a spacecraft. While politically and environmentally problematic near Earth, this technology might be viable for deep space missions. A nuclear pulse spacecraft could reach Saturn in less than a year, Neptune in under 3 years. The journey times that seem fixed by chemistry and physics might yield to the brute force of nuclear energy. The cultural impact of these long journey times shapes how we think about space exploration. Movies and TV shows compress interplanetary travel to minutes or hours, creating unrealistic expectations. When people learn it takes years to reach Jupiter, not hours, it can be deflating. But there's also something profound about the real timescales. They remind us that space is vast, that the universe doesn't conform to human convenience, that some things are worth waiting for. Consider how these journey times affect our search for extraterrestrial intelligence. If an alien civilization exists on a moon of Saturn and we detect their signals today, any response would take years to deliver. A conversation would span decades. This might explain the Fermi paradox. The universe might be full, of civilizations, but the distances and time delays make communication nearly impossible. We're all isolated by the vast emptiness between worlds. The psychological concept of overview effect, the profound shift in awareness astronauts experience seeing Earth from space, might have an opposite when Earth becomes invisible. What happens to human psychology when Earth is just another star, indistinguishable from thousands of others? Crews traveling to the outer planets will experience isolation no human has known. We're not just traveling through space, we're traveling through solitude on a scale that challenges human nature itself. Educational initiatives must adapt to these timescales. A student inspired by a launch to Neptune in elementary school might have their own children by the time the spacecraft arrives. Space agencies are developing educational programs that span entire academic careers, maintaining engagement across generations. Time capsule messages, where students write to their future selves to be opened when missions arrive, help bridge these temporal gaps. The preservation of knowledge across these mission timescales presents unique challenges. Technologies become obsolete, programming languages forgotten, and the engineers who built systems retire or pass away. NASA maintains archives of old computer systems just to communicate with spacecraft launched decades ago. The Voyager spacecraft, for instance, use computer systems with less processing power than a modern car key fob, yet we must maintain the expertise to operate them for as long as they continue functioning. This creates an interesting phenomenon, technological archaeology within active missions. Engineers working on Voyager today must understand 1970s technology, like digital archaeologists decoding ancient systems that are still operational. When these spacecraft eventually fall silent, we'll lose not just the missions, but the specialized knowledge of how to communicate with humanity's most distant ambassadors. Let me tell you about something that puts these journey times in a deeply personal perspective. When Carl Sagan was working on the Voyager mission in the 1970s, he included a golden record containing sounds and images from Earth. He knew that by the time Voyager reached the outer planets, years would have passed. His own son, Nick, recorded his voice as a child for the golden record. By the time Voyager reached Neptune, Nick was an adult with his own career. The spacecraft carried his childhood voice into interstellar space while he aged on Earth, a poignant reminder of how these missions span human lifetimes. The concept of mission heritage becomes crucial for long-duration exploration. Lessons learned from Voyager informed Galileo. Galileo informed Cassini. Cassini is informing Europa Clipper and future missions. This accumulated knowledge passed down through generations of spacecraft and scientists represents humanity's growing expertise in deep space exploration. Each mission builds on decades of previous experience, turning impossible journeys into merely difficult ones. Now consider the philosophical implications of these journey times. When we send a spacecraft to Pluto, we're essentially sending a message to our future selves. The scientists who will analyze the data might not even be born yet when the mission launches. We're engaging in a collaboration across time, trusting future generations to complete what we start. It's an act of faith in humanity's continuity and progress. The development of quantum communication, while still highly theoretical for practical applications, might revolutionize deep space missions. Quantum entanglement could potentially allow instantaneous communication across any distance, eliminating the hours-long delays that plague outer planet exploration. Imagine controlling a rover on Titan in real time, or having a conversation with astronauts orbiting Neptune without delay. While this remains in the realm of speculation, the mere possibility drives research that might yield unexpected breakthroughs. The journey times to different planets create a natural hierarchy of exploration. The Moon, just 3 days away, serves as our training ground. Mars, 6 to 9 months away, represents our first real interplanetary challenge. Jupiter and Saturn, years away, test our ability to sustain missions over long durations. Uranus and Neptune, requiring decades of commitment, represent the ultimate test of human persistence and planning. This hierarchy shapes funding priorities and public interest. It's easier to maintain enthusiasm for a Mars mission that delivers results in months than a Neptune mission that won't arrive until today's toddlers are teenagers. Space agencies must balance quick wins that maintain public support with long-term missions that advance fundamental science. The journey times become a political and social challenge as much as a technical one. Climate change on Earth adds urgency to understanding other planets. Venus shows us the extreme greenhouse effect. Mars demonstrates what happens when a planet loses its atmosphere. The ice giants reveal atmospheric dynamics we're only beginning to understand. But studying these planetary laboratories requires those long journeys. The lessons that might help save Earth are written in the atmospheres and surfaces of worlds that take years or decades to reach. The possibility of discovering life elsewhere in our solar system makes these journey times particularly frustrating. We might be just years away from answering one of humanity's most profound questions. Are we alone? But those years stretch into decades when you factor in travel time. If life exists in Europa's ocean or Enceladus's geysers, it's waiting there right now, just years of space travel away. The universe's speed limit turns what should be a sprint into a marathon. Here's something that showcases human creativity in dealing with these distances: the concept of cycler orbits. Buzz Aldrin, the second person to walk on the Moon, proposed spacecraft that continuously cycle between Earth and Mars, never stopping at either. Smaller, faster ships would rendezvous with these cyclers, transferring crew and cargo. It's like a train that never stops, with passengers jumping on and off at stations. This could make regular Mars travel more feasible, turning a difficult journey into a routine commute. The miniaturization of technology helps offset long journey times. Where we once needed room-sized computers, we now have smartphone-sized devices with greater capability. Smaller, lighter spacecraft can be accelerated to higher speeds with the same amount of fuel. CubeSats, satellites the size of a shoebox, are revolutionizing space exploration by making missions cheaper and faster. A swarm of CubeSats could explore multiple destinations simultaneously, multiplying our exploration capability. Breakthrough propulsion. Physics, a NASA program that ended in 2002, investigated exotic concepts like warp drives and wormholes. While these remain highly speculative, they represent humanity's refusal to accept the limitations imposed by conventional physics. Even if faster-than-light travel proves impossible, the research might yield unexpected discoveries that dramatically reduce journey times within the bounds of known physics. The role of private citizens in space exploration is evolving with these timescales. Crowd-funded missions, citizen science projects, and space tourism are democratizing access to space. While a ticket to Mars remains out of reach for most, thousands of people contribute to missions through distributed computing projects that analyze data from distant spacecraft. You might not be able to travel to Jupiter, but you can help discover new moons or analyze atmospheric data from your home computer. The development of self-replicating probes, while still theoretical, could transform solar system exploration. Imagine sending a single probe to the asteroid belt that mines materials to build copies of itself. These copies spread throughout the solar system, exploring multiple destinations simultaneously. What would take centuries with individual missions could happen in decades with self-replicating technology. Of course, this raises concerns about runaway replication and space pollution, issues we'll need to address before deploying such technology. Virtual reality and telepresence might make journey times feel shorter for future astronauts. Instead of staring at metal walls for years, crews could explore virtual worlds, maintain virtual presence on Earth, or even control robots on their destination planet before arriving. The physical journey might take years, but the psychological experience could be made rich and varied. We're not just transporting bodies through space, but minds that need stimulation and connection. The discovery of water ice throughout the solar system has revolutionized our thinking about journey times. Water can be split into hydrogen and oxygen, rocket fuel. The Moon, Mars, Ceres, Europa, Enceladus, and even some asteroids have water ice. Each could become a fuel depot, allowing spacecraft to travel faster by not carrying all their fuel from Earth. The solar system might become a network of oases, each making the next destination a little closer. Consider the impact of life extension technology on space exploration. If medical advances allow humans to live healthy lives for 200 years or more, suddenly a 20-year journey to Neptune doesn't seem as daunting. It would be like asking someone today to commit to a 2-year journey, long but manageable. The convergence of biological and space technology might make the entire solar system accessible within a single, extended lifetime. The concept of precursor missions helps manage long journey times. Before sending humans or complex rovers, we send simple orbiters to map and study destinations. These precursors identify landing sites, characterize hazards, and even cache supplies for future missions. By the time the main mission arrives years later, the destination is well understood and prepared. It's like sending scouts ahead of an expedition, making the journey safer and more productive. The social implications of these journey times shape how we think about space colonization. A Mars colony, reachable in 6 to 9 months, could maintain strong cultural and economic ties with Earth. But a colony on Titan, requiring 7 to 10 years of travel, would develop its own culture, possibly diverging from Earth in fundamental ways. The distance wouldn't just be physical, but cultural, creating human societies as alien to us as the worlds they inhabit. This cultural divergence isn't necessarily negative. Isolated human populations throughout history have developed unique solutions to challenges, enriching humanity's collective knowledge. Colonies in the outer solar system might develop technologies and philosophies we can't imagine, shaped by their unique environments and isolation. The journey times that seem like barriers might actually be creating laboratories for human innovation and adaptation. Let me share something that illustrates how journey times affect mission design. When planning the Cassini mission to Saturn, engineers had to predict what questions scientists would want to answer, not when they designed the instruments in the 1990s, but what they'd want to know in the 2010s when the spacecraft arrived. They had to anticipate decades of scientific progress and design flexible instruments that could address questions they couldn't even formulate yet. The concept of gravitational highways or the interplanetary transport network reveals hidden shortcuts through the solar system. These are paths where the gravity of multiple bodies creates low-energy routes between planets. Following these paths takes longer but requires minimal fuel. A spacecraft could drift from Earth to Mars using almost no propulsion, though the journey might take years instead of months. It's like finding ocean currents that carry ships with minimal effort. The development of artificial consciousness raises intriguing possibilities for long-duration missions. An AI that experiences time differently than humans might not find a decade-long journey to Neptune tedious. It could conduct observations, make decisions, and even experience something analogous to curiosity and wonder without the psychological challenges that would affect human crews. We might be creating not just tools for exploration, but new kinds of explorers adapted to the vast scales of space. Space weather adds another variable to journey times. Solar flares, cosmic radiation, and the solar wind affect spacecraft trajectories and systems. A mission to Mercury must account for intense solar radiation, a mission to the outer planets must deal with weakening solar power and increasing cosmic radiation. These factors don't just affect journey duration, but determine when missions can safely launch. We're not just navigating space, but navigating the sun's changing moods. The concept of terraform forming takes on new meaning when considering journey times. We might not transform entire planets, but create small, habitable spaces, caves on Mars, domes on the Moon, or floating habitats in Venus's atmosphere. These wouldn't be new Earths, but rather oases that make long journeys bearable. A network of such habitats throughout the solar system would make it feel smaller, more accessible, more human. Here's a sobering thought about the distances involved if something went catastrophically wrong on Earth: asteroid impact, nuclear war, or runaway climate change. Our furthest human outposts would be mere months away on Mars, maybe years away if we had bases on Jupiter's moons. We wouldn't have truly backup locations for humanity, just distant camps that would struggle to survive without Earth's support. The journey times that frustrate our exploration also limit our ability to spread beyond Earth as insurance for our species. The evolution of space law and governance must account for these journey times. How do you govern a colony that's hours away by communication and years away by travel? Current space law, based on maritime and Antarctic treaties, assumes relatively quick access and communication. But a colony on Titan might need near-complete autonomy, developing its own laws and governance structures. The distance creates not just physical but legal and political separation. Consider how these journey times affect resource allocation. Every kilogram sent to Mars costs thousands of dollars. Every kilogram sent to Jupiter costs tens of thousands. Every kilogram sent to Neptune costs hundreds of thousands. This economic gradient means outer solar system missions must be increasingly selective about what they carry. A wrench sent to Neptune is worth its weight in gold, literally, by the time you factor in launch and journey costs. The development of in-space manufacturing could revolutionize this equation. Instead of sending finished products on years-long journeys, we might send manufacturing equipment and raw materials, or better yet, use materials found at the destination. 3D printing technology is already being tested on the International Space Station. Future missions might carry printers capable of producing everything from tools to habitats using local materials. The psychological concept of time perspective becomes crucial for long missions. Humans typically think in terms of days, weeks, or months, occasionally years. But space exploration requires thinking in decades. Space agencies are working with psychologists to understand how to maintain motivation and mental health over such extended timescales. It might require fundamental changes to how we structure goals, rewards, and social connections. The discovery of extremophiles, organisms that thrive in extreme conditions on Earth, gives us hope for finding life despite the long journeys required to search for it. If life can exist in boiling acid pools or miles beneath Antarctic ice, it might exist in Europa's ocean or Titan's hydrocarbon lakes. Every year we wait to explore these worlds is a year we might be missing evidence of life. The journey times aren't just frustrating, they're delaying potentially the greatest discovery in human history. Nuclear fusion, when it finally becomes practical, will transform these journey times. A fusion rocket could maintain acceleration for months or years, building up enormous speeds. A trip to Mars might take weeks instead of months. Jupiter could be reached in less than a year, Neptune in under 4 years. The technology that might solve Earth's energy crisis could also open up the entire solar system to routine exploration. The role of international cooperation becomes even more critical as we venture farther out. No single nation has the resources or expertise to mount regular missions to the outer planets. The International Space Station has proven that former adversaries can work together in space. Future missions to Uranus or Neptune will likely require even broader coalitions. possibly including private companies and universities. The distances that challenge us technically might unite us politically. Let me tell you about a concept that could change everything. The breakthrough propulsion physics we need might come from studying the universe itself. Dark energy, which makes up 68% of the universe and drives its accelerating expansion, remains completely mysterious. If we could harness even a tiny fraction of dark energy, journey times might become irrelevant. The force that's pushing galaxies apart might one day push our spacecraft to the stars. The possibility of hibernation or suspended animation for human crews isn't just science fiction anymore. Scientists have successfully induced hibernation-like states in mammals that don't naturally hibernate. For a journey to Neptune, putting the crew in suspended animation for the bulk of the journey might be more practical than trying to maintain a fully active crew for 15 years. You'd wake up at your destination as if only weeks had passed, though years would have elapsed on Earth. Robotic precursors will always travel ahead of humans, and as AI improves, these robots become increasingly capable. By the time humans arrive at Mars, robots will have been exploring it for decades. By the time humans reach Jupiter's moons, robots will have mapped every crater and analyzed every interesting site. The long journey times mean humans will always arrive at well-studied destinations, trading the excitement of first discovery for the safety of thorough preparation. The concept of generation ships for interstellar travel might first be tested within our solar system. A large, self-sustaining spacecraft traveling to Neptune over 15 to 20 years could serve as a prototype for eventual interstellar missions. The children born during the journey would know no world but their ship, creating a unique culture adapted to life in space. It sounds extreme for exploring our own solar system, but it might be necessary practice for reaching the stars. Time itself becomes fluid when dealing with these scales. A mission launched today to study Neptune up close won't return data until many of us are gone. We're participating in a conversation with the future, sending questions that our descendants will receive answers to. It's humbling and inspiring. We plant trees whose shade we'll never enjoy, launch missions whose results we'll never see, all for the advancement of human knowledge. The development of closed-loop life support systems for these long journeys has Earth applications too. Technologies developed to recycle air, water and waste on a 15-year journey to Neptune could help create sustainable communities in Earth's deserts or polar regions. The challenge of keeping humans alive on long space journeys might teach us how to live more sustainably on our home planet. Here's something that captures the strange reality of these journey times. When New Horizons flew past Pluto, it was traveling so fast, about 31,000 miles per hour relative to Pluto, that the entire close encounter lasted less than a day. We waited 9.5 years for 24 hours of close observations. It's like driving across the country to watch a sunset. The journey dominates the experience, but those brief moments at the destination make it all worthwhile. If you made this far, make sure to subscribe to the channel and give a thumbs up. Also, I am sure you will love this other video at the left side of the screen. This is why we will never leave the solar system. In this video, discover the real science behind our cosmic confinement and the fundamental barriers that make interstellar travel impossible. See you there.